JIT, just in time, and lean manufacturing both aim to deliver the right product in the right quantity at the right time while eliminating waste. Historical roots: Toyota Production System, TPS, in the 1940s to 1960s introduced JIT as a response to limited post-war resources. In the 1980s, Western scholars Womack, Jones, and Roos coined lean to describe the broader philosophy of waste reduction, muta, unevenness, mura, and overburhead, muri. Core principles: value defined by the customer. Only activities the customer is willing to pay for are kept. Value stream mapping: identify every step from raw material to delivery, then cut non-value adding steps. Flow: arrange steps so work moves continuously without waiting. Pull: produce only when downstream demand signals a need, Kanban. Perfection: a continuous improvement, Kaizen. These ideas evolved from batch and queue production to a synchronized, flexible system comparable to a well-orchestrated kitchen where each chef prepares a dish only when the order arrives. Lean tools give managers concrete ways to practice the 5 principles. Kanban: visual cards or electronic signals that tell a workstation when to start a new batch. Quantitatively, the number of cards N equals demand per period times lead time divided by lot size, ensuring work in process equals demand times lead time. Value stream mapping: VSM: a diagram that records process times T sub I and wait times W sub I, the process cycle efficiency. PCE equals the sum of T sub I divided by the sum of T sub I plus W sub I. Improving PCE shows how much waste is cut. 5S: sort, set in order, shine, standardize, sustain. The impact is measured by reduction in search time, for example minutes saved per shift, and defect reduction %. Kaizen: small daily improvements. A common metric is the cumulative cost saving equals the sum of baseline cost minus improved cost across all Kaizen events. Analogy: think of a home kitchen. Kanban is the sticky note that says buy milk when the fridge is empty. VSM is the recipe flow chart that shows preparation, cooking, and plating times. 5S is keeping the pantry organized. Kaizen is trying a new chopping technique to shave 30 seconds off preparation each day. Explanation: the economic order quantity, EOQ. Model assumes a fixed order size that minimizes total cost equal to ordering cost plus holding cost. EOQ formula: Q star equals square root of open bracket 2ds divided by h close bracket, where d equals annual demand, s equals setup ordering cost per order, h equals holding cost per unit per year. JIT: order size approaches 1 unit or the daily demand, making setup cost high but holding cost near 0. The total cost for JIT is TCJIT equals D times S daily plus 0 holding. Numerical illustration: assume D equals 12,000 units per year, S equals $50 per order, H equals $2 per unit per year. EOQ equals square root of open bracket 2 times 12,000 times 50, divided by 2 close bracket equals square root of 600,000, approximately 775 units. Total EOQ cost equals open bracket D divided by Q close bracket times S plus open bracket Q divided by 2 close bracket times H equals open bracket 12,000 divided by 775 close bracket times 50 plus open bracket 775 divided by 2 close bracket times 2, approximately $775 plus $775 equals $1,550. JIT daily lot equals 12,000 divided by 250, approximately 48 units, with daily setup S sub D equals $50. Holding approximately 0, TCJIT, approximately 250 times 50 equals $12,500. Thus EOQ beats JIT when setup is costly and holding is cheap. However, if holding cost rises to $10 per unit, EOQ cost becomes $6,250, while JIT remains $12,500, showing the trade-off. The MBA student should be able to set up the cost function, differentiate, and solve for optimal Q, then compare to a JIT scenario. Takt time is the pace at which the market demands the product. T equals available production time divided by customer demand. For an 8-hour shift, 480 minutes, and daily demand of 240 units, T equals 2 minutes per unit. Hijunka, also called level loading, spreads production evenly to avoid peaks. Suppose 3 product variants A, B, and C require 1 minute, 2 minutes, and 1 minute per unit respectively, with daily demand 150 and 150 units. Total minutes equals 100 times 1 plus 50 times 2 plus 150 times 1 equals 400 minutes, which is well within 480 minutes. A Hijunka board schedules mixed cells, so each 2-minute slot produces either A, B, or C according to the ratio 4 to 2 to 6. Linear programming example. Minimize total idle time Z equals the sum over slots of T minus the sum over products of P sub ij times X sub ij subject to the constraints that the sum over J of X sub ij equals D sub I, the demand for each product I. The sum over I of P sub ij times X sub ij is less than or equal to T, the capacity per tax slot, and X sub ij is greater than or equal to 0. Solving yields the exact number of each product per slot, demonstrating how mathematics guarantees a feasible leveled schedule. Analogy: imagine a subway train that leaves every 5 minutes, which is the takt. Hijunka is like assigning passengers different product types to each car so no car is overloaded and the train runs smoothly. In a JIT environment, the 3 classic inventory costs behave differently. Setup ordering cost S. Each time a small lot is produced, a setup is required. If daily demand equals D, number of setups per year equals D divided by D. Total setup cost equals D divided by D times S. Holding cost H with near 0 work in process. Average inventory approximately D divided by 2 if we assume a tiny batch. Holding cost equals D divided by 2 times H times N days. Often this term is negligible. Shortage stock out cost C sub SJIT reduces safety stock, so the risk of stock out rises. Expected shortage equals probability of demand greater than supply times shortage penalty. Sample calculation. D equals 10,000 units per year, daily demand D equals 40 units, S equals $30, H equals $1 per unit per year, shortage penalty equals $5 per unit missed. Setups per year equals 10,000 divided by 40 equals 250. Setup cost equals 250 times 30 equals $7,500. Average inventory approximately 20 units. Holding cost equals 20 times 1 equals $20. Assume a 2% chance of a stock out of 1 unit each time. Expected shortage cost equals 0.02 times 10,000 times 5 equals $1,000. Total JIT cost approximately $8,520. This illustrates why managers must balance the cheap holding cost against higher setup and possible shortage costs. Key performance indicators translate lean ideas into numbers. Overall equipment effectiveness, OEE, equals availability times performance times quality. Example, availability equals 90%, downtime 10% of scheduled time, performance equals 95%, speed 5% slower than rated, quality equals 98%, 2% defective. OEE equals 0.9 times 0.95 times 0.98, approximately 0.84 or 84%. Process cycle efficiency, PCE, equals value adding time divided by total cycle time. If a part spends 3 minutes in machining value and 12 minutes waiting or transport, PCE equals 3 divided by 12 equals 25%. Lead time reduction, lead time equals processing time plus waiting time. A Kaizen reduces waiting from 8 to 4 days. Lead time drops from 12 to 8 days, a 33% reduction. Analytical example, a widget line produces 1,000 units per week. Machine runs 40 hours per week. Downtime equals 4 hours, speed equals 0.9 of design rate equals 30 units per hour, defects equal 5%. Availability equals 40 minus 4 divided by 40 equals 0.90. Performance equals 30 times 0.9 divided by 30 equals 0.90. Quality equals 1 minus 0.05 equals 0.95. OEE equals 0.90 times 0.90 times 0.95 equals 0.77, 77% of theoretical output. These metrics give MBA students a quantitative basis to argue for line investments. Explanation: a disciplined rollout helps avoid the common pilot then die syndrome. Roadmap 8 steps. 1. Leadership commitment CEO sponsor, clear vision statement. 2. Current state assessment VSM, KPI baselines. 3. Target state definition future state VSM, TAC time OEE goals. 4. Training and culture building Kaizen workshops, 5S drills. 5. Pilot project choose a low-risk cell, apply Kanban, measure results. 6. Standardization document SOPS, visual controls. 7. Scale out replicate pilot learnings, adjust for product mix. 8. Sustainability audits, continuous improvement board reward system. Change management tips. Use Cotter's 8-step model, create urgency, form coalition, etc. Address employee fear by involving them in problem solving and communicate quick wins. Exam type scenario. A midsize auto parts maker wants to reduce inventory. As the operations manager, outline the first 3 actions you would take and explain how you would measure success after 6 months. Students should mention leadership buy-in, current state VSM, pilot selection, and KPI such as inventory turns, lead time, OEE. Success factors. Strong top management support. Clear customer-focused value definition. Visible visual management, Kanban boards and Andon lights. Cross-functional Kaizen teams. Continuous training and skill development. Common pitfalls. Over-reliance on technology without cultural change. Implementing tools in isolation, for example 5S only. Ignoring variability Mura leading to bottlenecks. Setting unrealistic zero inventory goals causing stock outs. Failing to protect the pilot area from normal production pressure. Risk mitigation. Start with a short, well-defined pilot and protect its resources. Use statistical process control to monitor variability early. Maintain a minimal safety stock for critical items. Conduct regular Gemba walks to catch resistance early. Align incentive systems with lean metrics, for example OEE bonuses. Explanation. A side-by-side cost-benefit comparison clarifies the strategic choice. Traditional mass production. High batch sizes lead to low setup cost per unit. High holding cost H times average inventory. TC mass equals D divided by Q times S plus Q over 2 times H. Lean production. Small batches result in higher setup cost, negligible holding cost, possible shortage cost C sub S. TC lean equals D divided by Q times S plus C sub S. Decision tree simplified. Is setup cost S less than H times Q squared over 2D? If yes, mass production cheaper. Is customer lead time critical greater than 30 days? If yes, lean favored despite higher S. Evaluate risk of stock out C sub S using demand variability sigma. Numerical example. D equals 24,000, S equals $40, H equals $3, safety stock cost $2 per unit. Economic order quantity mass equals square root of 2 times 24,000 times 40 divided by 3, which equals square root of 640,000, equals 800 units. Total cost mass equals D divided by 800 times 40 plus 800 over 2 times 3, which equals $1,200 plus $1,200 equals $2,400. Lean lot equals 100 units daily. Setups equal 240. Total cost lean equals $9,600 plus shortage $300 equals $9,900. If the market pays a premium of $10 per unit for faster delivery, extra profit equals 24,000 times $10, which is $240,000, easily outweighing the $7,500 extra cost, making lean the better strategic choice. This quantitative framework helps MBA candidates justify lean in a business case presentation. Conceptual 10 points. Define the 5 core principles of lean manufacturing and explain how each contributes to waste reduction. Provide a real-world example for 2 of the principles. Model answer. Lists value, value stream, flow, pull, perfection. Explains waste types muta, mura, muri. Example, pull in a fast food kitchen, flow in an assembly line. Scoring rubric. 2 points per principle, 10 points total, plus 2 points for each concrete example, maximum plus 4 points. Deductions for vague or missing elements. Quantitative EOQ versus JIT, 15 points. A company sells 15,000 units per year. Setup cost $60 per order, holding cost $4 per unit per year. Calculate EOQ and total cost. Then assume a JIT policy with daily orders approximately 41 units and the same setup cost. Compute total cost ignoring holding cost. Which policy is cheaper? Show all steps. Model answer. EOQ equals square root of 2 times 15,000 times 60 divided by 4, approximately 212. Total cost EOQ equals 15,000 divided by 212 times 60 plus 212 divided by 2 times 4, approximately $4,250. JIT cost equals 15,000 divided by 41 times 60, approximately $22,000. EOQ cheaper. Rubric: 4 points for formula, 4 points for calculation, 4 points for interpretation, 3 points for presentation and units. Linear programming Hijunka 20 points. Given 3 products with processing times 1, 2, and 1 minute and daily demand 120, 60, 180 units respectively, formulate a linear program to minimize total idle time over an 8-hour shift. Solve for the number of each product per 2-minute task slot. Model answer. Define variables XA, XB, XC per slot. Constraint sum of time I times XI less than or equal to 2, sum of XI equals 1 product per slot over 240 slots. Solution XA equals 0.4, XB equals 0.2, XC equals 0.4, schedule 4A, 2B, 4C per 20 slots, etc. Rubric: 5 points for problem formulation, 5 points for constraints, 5 points for solution method simplex or logic, 5 points for interpretation. Change management 10 points. List and briefly describe Cotter's 8 steps for implementing Lean in a mid-size manufacturing firm. Model answer. Step 1, create urgency. Step 2, form powerful coalition. Step 3, create vision. Step 4, communicate vision. Step 5, empower action. Step 6, generate short-term wins. Step 7, consolidate gains. Step 8, anchor changes. Rubric: 1 point per step correctly named and described, maximum 8 points, plus 2 points for clarity. Critical thinking 15 points. Discuss 2 major risks of adopting a pure JIT system in a supply chain prone to disruptions, for example natural disasters. Propose mitigation strategies. Model answer: risks, stockout risk, high setup cost. Mitigations: safety stock for critical parts, dual sourcing, flexible contracts, buffer time and schedule. Rubric: 4 points per risk, 8 points total, 4 points per mitigation, 8 points total, 1 point for overall coherence. These questions test both conceptual understanding and quantitative application, mirroring typical MBA operations management exams. From this explanation, you just need to break them into segments, and for each segment return phonetic reading style of the segment. The output should be formatted as a JSON instance that conforms to the JSON schema below.